Thank you very much, and thank you very much for inviting me to this great conference here. So I will speak about joint work with Toby G, Tong Liu, and David Savitt. So K will be a finite extension of QP, and GK will denote the absolute Galois group of K. And then in general, one can ask some questions about liftability of mod P Galois representations of such a group. So question number 1. Given rho bar a mod P n-dimensional Galois representation, does there exist a lift to characteristic 0? And this is not known. So let me say what a naive strategy to solve such a question would be. So given any mod P Galois representation, it's, excuse me? It means the ring of integers of QP bar, and FP bar is the residue field. So the naive strategy would be rho bar can be written in the form V1 bar up to VL bar, where each VI bar is irreducible. And then you could imagine trying to lift each VI bar. So try to find rho of the form V1 up to VL, where each VI lifts VI bar. And then this doesn't naively work because there's an obstruction whenever, from local Galois cohomology, whenever VI bar is isomorphic to Vj bar twisted by cyclotomic character for some I less than j. But of course, you have a lot of freedom to choose the VIs, and even though you might have an obstruction for a particular choice of lift, maybe some other lift will work, and I don't actually know whether, I don't know any counter example to this not working. Yes, irreducible ones, it's easy, and that will come up. Yeah, that will come up later on, in fact. And now, question 2. One can ask stronger questions. One can ask various forms of this question. So question 2, in question 1, can we even demand that rho bar, that rho is Theorem? And maybe more interestingly, with distinct Hodge Tate weights. So this, of course, implies question 1. And then, even more strongly, one could ask question 3, which implies question 2, whether in question 1 we can demand that rho is, and I will recall what it means, potentially diagonalizable and regular. And this, in fact, was conjectured in earlier work by Emerton and G. So regular means that all the Hodge-Tate weights are distinct. In fact, for each different embedding of k into QP bar, one has a set of n Hodge-Tate weights, and they're all distinct. What does potentially diagonalizable mean? Recall, this notion was first defined by Barnett, Lamb, G, Garrity, and Taylor in their work on potential automorphy, that rho is potentially diagonalizable if there exists a finite extension k prime of k such that when we restrict rho to the Galois group of k prime, it's crystalline, and it lies on the same component of the crystalline deformation ring for the reduction of this representation as a diagonal representation. So, and it lies on the same component. As a diagonal representation on Kissin's crystalline framed deformation ring. Of fixed Hodge type, namely the one of rho, restricted to gk prime. And the reduction of rho, restricted to gk prime. So this notion is very useful from the point of view of what the best automorphy lifting theorems can do at the moment, because this condition at P allows one to, sort of the hardest abstraction, the hardest difficulty that remains for, in the self-dual case at least, for potential automorphy theorems for automorphy lifting theorems is one gets from the Taylor-Wiles-Kissin method that the union of components of the deformation ring, or the generic fiber of such a deformation ring, which arise from automorphic representations, is a union of components, and this condition allows one to pass from one component to another component, roughly speaking. So it would be very useful to know that any potentially crystalline representation is potentially diagonalizable. And equally well, it would be very useful to know that any rho bar has a potentially diagonalizable regular lift. So what is known? So question 3 is true. So there are some simple cases that were discussed in the paper where the notion was defined. So rho bar is semi-simple. So this is again because irreducible representations can be lifted easily to characteristic 0, as I'm going to mention again more explicitly later on, or when the dimension is at most 2, or when k is an unramified extension and rho bar is Fontaine-Laffaille. In which case the deformation ring just has one is irreducible. So this was Barnett, Lamb, G, Garrity, and Taylor. And then it's also true when n is equal to 3. So when n is equal to 3, and this was proved in the thesis of Alain Müller a couple of years ago. Okay, so in order to state our first result, I need to make a definition. So we will say that rho bar, as above, is peu ramifié. If the following condition holds, so there exists a filtration, an increasing filtration, 0 equals U0 bar, contained in U1 bar up to UL bar, which is rho bar, such that first of all, the graded pieces are irreducible. Ui bar modulo ui minus 1 bar irreducible for all I. And I'll call that vi bar. And secondly, the class of ui bar in the x1 between, so let me write it as an h1 gk vi bar ui minus 1 bar. So the extension class that ui bar defines is annihilated by all unramified classes in the dual H1. Under Tate local duality. So in H1 GK ui minus 1 bar to vi bar twisted bicyclotomic. I mean those classes that arise by, well, you can say that restrict trivially to inertia. So if you have a restriction map to H1 of inertia, and this is the unramified classes is the kernel of this map. Right, so I will make a remark about this in a moment. Yeah, I mean, this is maybe not the best possible abstract definition of what it means to be peu ramifié, but it works well for our purposes. So I will make a few remarks now, just on the notion of peu ramifié. So first of all, in the two-dimensional case, this is just the usual notion. So we have an extension of chi by chi omega, the cyclotomic character. Then this one is peu ramifié in the sense over on the left, if and only if it is peu ramifié in the classical sense. So this is the usual definition. This is the usual definition, equivalent to the usual definition. And any other two-dimensional Galois representation, one that is not an extension of chi by chi omega, is automatically considered peu ramifié here. And more generally, if ui minus 1 bar does not surject onto the irreducible representation vi twisted by cyclotomic, in particular, if vj bar is not isomorphic to vi bar twisted by cyclotomic for all j less than I, then rho bar is automatically peu ramifié. And the reason is that there are no unramified classes in this case. So let me just remind you that the unramified classes in GK with coefficients in X are just the kernel of the restriction map to inertia, which is the same as the classes arising by inflation from GK mod IK of X IK invariance, and that has the same dimension. So maybe let me write lower H1 for dimension. Here we have a cyclic procyclic group, so we get this is the same as H0 of GK mod IK XIK, which is just the H0 for GK on X. And in this case, under the assumption, it's 0. Thirdly, if K over QP is unramified and rho bar is Fontaine-Laffaille, then it is peu ramifié. And for this, I will discuss later. And finally, so this comes back to your question. So the above definition is sensitive to the choice of filtration. And here's a simple example. So if we take rho bar three-dimensional of the form omega C1, 1, 1, C2, where I assume that omega is not trivial, equivalently that K does not contain the pth roots of unity, and C1 is non-split peu ramifié, and C2 is très ramifié in the usual senses as an extension of omega and the trivial character. Then if we take the filtration to be the standard one on this basis, it is peu ramifié because clearly it's the case for the first two-dimensional piece, and then for the second one too, because for the last step too, because by remark 2 it follows, because this representation, if it's non-split, doesn't have a cyclotomic quotient. But on the other hand, we can rewrite this by interchanging the second and third column. And now it's clear it's not peu ramifié. So this is, yeah, maybe I will not write that sentence. Sorry? Well, peu ramifié is kind of dual to unramified. Yes. Right. I agree. I think this is a counterexample. I mean, in general, for our purposes, it would. Right. But I think if you dualize, you have omega inverse at the end, right? Oh, but you also dualize the filtration. Yeah. Yeah, maybe contragradients are okay if you also dualize the filtration at the same time. But in any case, for our purposes, we could also allow different ways to go up. I mean, instead of going up the filtration, maybe going. Anyway. Well, let me maybe comment when we actually when I actually get to proofs. So, all right, and so let me let Sk be the set of embeddings of K into QP bar. So QP linear maps. Then our first theorem says that if rho bar is peu ramifié, then it has a lot of regular potentially diagonalizable lifts. So then it has a regular plus potentially diagonalizable lift, rho, and there are many such. For example, we could demand also that, part 1, that rho is crystalline, and you could also bound the range of Hodge-Tate weights, although maybe we haven't written a precise statement of that yet, so let me not say anything completely precise here, how far you can bound it. And secondly, that rho has an alternative kind of lift you can make is that rho has Hodge type 0, which means that for each embedding sigma, so for all sigma in Sk, you get a set of n Hodge-Tate weights, and Hodge type 0 would be all of them are 0, 1, up to n minus 1. And in fact, it could be arbitrary. You could prescribe regular Hodge Tate weights in each embedding. Doesn't matter, but let me, for the sake of writing it down, let me stick to the simplest case. And rho becomes crystalline over some finite extension k prime over k, which doesn't depend on rho bar, but only on n and k. So that depends only on n and k. Okay. So one remark is that in the situation of remark 2, this is obvious. We don't. I mean, this is an example where rho bar is automatically pyramify, but this is also an example where it's very easy to prove theorem 1 because there are no obstructions to lifting. But the second remark is that if k over qp is unramified and rho bar is Fontaine-Laffaille, then the second part of this theorem has applications to GL2 cross GLN to GL2N functionality in work in progress, so it doesn't exist yet, of Arias de Reina and Diolefin. Okay, so next I want to state two more kind of theorems that we can prove, and they are about congruences when we assume that rho has one kind of the Rham lift to produce other kinds of the Rham lifts. So theorem 2. In fact, the Fontaine-Laffaille, if you apply this theorem in the case of a Fontaine-Laffaille rho bar, then it's already a kind of congruence theorem. So now, if rho bar has a regular, potentially diagonalizable lift, and p does not divide to n, then rho bar has a crystalline lift, has a regular crystalline lift. And one can bound, one can restrict the Hodge type, so with a restricted range of Hodge Tate weights. And the second theorem in this spirit is giving some rather weak evidence for the Breuer-Messar conjecture. So if lambda is an n-tuple of integers, is a collection of n-tuples of integers indexed by the embeddings of k into qp bar, such that for each sigma we get a dominant weight. So lambda sigma 1 is greater or equal to lambda sigma n. Let L sub lambda be the algebraic representation of the restriction of scalars of GLN of this highest weight. So explicitly, let me write it this way. It's a tensor product over sigma and sk of L lambda sigma tensored from K to QP bar via the embedding sigma, where L lambda sigma is the irreducible representation of the algebraic group GLN over K of highest weight lambda sigma. And if tau, a second piece of notation, if tau is a Galois type, so in other words, an n-dimensional representation of the inertia subgroup that extends to the Galois group, so is a Galois type, i.e. extends, permits an extension to GK, and is a finite image, then a version of the inertial local Langdon's correspondence gives an irreducible representation. So really this reposes on work of Schneider and Zink, irreducible representation of GLN OK over QP bar. So associated by inertial local Langdon's correspondence. Okay, so now I can state the theorem. So theorem 3. Suppose K over QP is unramified and P is greater than N. And suppose that rho bar has a particularly simple kind of crystalline lift, namely of very low weight. Suppose rho bar has a crystalline lift of Hodge type. In the Fontaine-Laffaille range. So of Hodge type lambda prime as above. So it lies in the same set as above, such that lambda prime sigma 1 minus lambda prime sigma n is less than or equal to p minus n for all sigma. Then the representation L lambda prime defined up here has an irreducible reduction as GLN OK representation. Well, this is well known, but it's just needed to make the rest of the sentence have more sense. So, and for all pairs lambda comma tau as above, such that if you take L lambda tensor L tau and you reduce it modulo P, this irreducible representation L lambda prime reduced mod P occurs inside as GLN OK factor, subquotient, then rho has a potentially crystalline lift of type lambda comma tau. In other words, it has Hodge-Tate weights prescribed by lambda. So really, the lambda i's are shifted by n minus 1, n minus 2, and so on. So Hodge-Tate weights at sigma, lambda sigma comma 1 plus n minus 1, down to lambda sigma comma n minus 1 plus 1, lambda sigma comma n for all sigma. There's no restriction on lambda and tau. And the Wedelin representation associated to to such a lift, then rho bar has a lift rho. On inertia, it's equal to tau. So this is a particularly simple, this is a simple special case of the Brahmi-Sar conjecture, which does not just say, it says something more about how many about deformations, about the deformation ring for this type, lambda and tau, not just the existence of a lift. So this is as predicted. By the Brahmi-Sar conjecture. So let me just sketch the proof of the theorems 2 and 3. And then I will go back to theorem 1. So in either case, so the proof of theorems 2 and 3 are of global nature. So in either case, rho bar has a potentially diagonalizable regular potentially diagonalizable lift. And then, so there's a sequence of works, I suppose, residing on the work, reposing on the work of BLGGT and also earlier work of Caligari, but the theorem we need is due to Emerton and G. So maybe I should write this out. Emerton, G, show that rho bar has a globalization in the context of unitary groups. Rho bar has a globalization. And moreover, due to the, so this doesn't actually need the assumption that the lift has any that rho bar has any properties at all. This uses theorems of Moret and Bailly. So rho bar and is due to Caligari. So rho bar has a globalization, but in this case, under the assumption of regular potentially diagonalizable, the lift, the globalization can moreover be taken to be automorphic. By refining some potential automorphic results in the paper of BLGGT. And now, once you have an automorphic globalization, then it's very easy to construct such lifts, actually. Because you have a space of automorphic forms with coefficients here, and then the coefficients lift, so you can lift the Hecke eigenvalues and use known results about Galois representations. So use congruences between automorphic forms on compact unitary groups. So this is the sketch, but the remark is that as opposed to theorem 1, in these two results, we cannot guarantee that the lift is potentially diagonalizable. That's actually automatic, because in this situation, we're in the Fontaine-Laffaille case, so by the previous remark, yes. So the remark is that this method, because unfortunately we don't know that any potentially crystalline representation is potentially diagonalizable. That rho is potentially diagonalizable. Okay, so the rest of the talk will be purely local. So I need to explain to you why theorem 1 holds, and also why everything Fontaine-Laffaille is pure ramifié. So proof of theorem 1. So we first have a proposition that if a representation is peu ramifié, so basically what we realized is that this peu ramifié condition is related to having many lifts. And there's in fact maybe I'll get that. I'll say more at the end. So if rho bar is peu ramifié, and we pick any lifts vi of vi bar, and vi lift vi bar, then there exist characters psi I from gk to zp bar cross that are unramified, reduced to the identity such that rho bar lifts to a representation of the form v1 twisted by psi 1 down to vl twisted by psi l, like that. So basically, twisting by such characters, well, first of all, it doesn't change the reduction of these representations, and second of all, if we have something crystalline, it doesn't mess with that either because it's unramified, nor with the Hodge-Tate weights. So moreover, there's a lot of choice for these characters psi I. So if we let capital psi denote the L tuples, L tuples psi 1, psi I equals 1 to L that work in this statement, then whenever we have chosen the first I characters, it can be extended to the I plus first in infinitely many ways. So whenever psi 1 up to psi I extend to an element of capital psi, then there exist infinitely many. So then there are infinitely many psi I plus 1, such that psi 1 up to psi I plus 1 extend to an element of capital psi. And the corollary is that if we're now in the situation that is useful for applications where the VIs are potentially crystalline, so if VI in the proposition are potentially crystalline with monotonic Hodge-Tate weights, in the sense that I'll write it in quotes. So each Hodge-Tate weight of each sigma Hodge-Tate weight of Vi is greater than each sigma Hodge-Tate weight of Vi plus 1 for all sigma and I, then we can demand, moreover, that for any finite extension k prime over k, if all is restricted to gk prime are crystalline, then so is the lift rho. And this is very easy to deduce from the previous proposition, because it's known that because of the monotonicity of the Hodge-Tate weights, that if we extend semi-stable representations, they are semi-stable. And by avoiding a finite collection, basically by avoiding some bad twists, you can also ensure that the extension is crystalline. One only really gets a problem when the things differ exactly by a cyclotomic character. So first I want to explain why the corollary implies the theorem, and then why the proposition holds. So now I get back to the irreducible representations and how to lift them. So the reason why we can lift the irreducible VI bars is simply that they're all induced. They're all induced from characters, so they're all of the form of some character chi I bar induced from an unramified extension. So ki over k is finite unramified, and chi I bar is a representation, is a character of gki. So now it's clear how to lift such representations to characteristic 0. And if we want to lift it to something crystalline, we just lift chi I bar to a crystalline character chi I. Such that if we let Vi denote the induced representation of chi I, then such that this induced representation is regular and the Hodge-Tate monotonicity holds. So it's regular and Hodge-Tate sigma Vi plus 1 is greater than Hodge-Tate sigma Vi for all sigma and I. It depends how you normalize your Hodge-Tate weights. So, oh, yes, I should at least be consistent. So this explains how we can lift to something crystalline, and now it's easy to see that we can such a lift will also be potentially diagonalizable, and the reason is that so we get the lift, we get the crystalline lift rho of the form V1 tensor psi 1 down to VL tensor psi L. Now, why is such a lift potentially diagonalizable? So rho potentially diagonalizable. The reason is simple, namely when we restrict Vi to some finite extension, it's a direct sum of characters, we can make the representation upper triangular. So let me write this down. So Vi restricted to gki is diagonal. So for some large extension k prime over k, we can ensure that rho restricted, this lift restricted to gk prime is upper triangular. And moreover, that rho bar restricted to gk prime is diagonal, even trivial. Then we can just deform the extension class to make, we can just rescale the extension class to make it go to 0. So then deform to a diagonal representation. This is already observed in BLGGT. Yeah, so once we have an upper triangular representation, it is potentially diagonalizable. And so for the second part of the theorem, how can we get a lift of Hodge type 0? So this is also not difficult. So choose auxiliary crystalline characters phi I of gki and now define theta I to be the Teichmüller lift of chi I bar times phi I bar inverse. So this is Teichmüller lift. Then this is a representation of GKI, which is potentially crystalline of Hodge type 0. So the reason is this is a representation that's a Teichmüller lift, so its image has order prime to p, so it's tamely ramified. And so inertia has finite image from class field theory, so it has to have Hodge type 0. And now let Vi be the induced representation of theta I times phi I. Then this reduces, so this lifts Vi bar clearly. And is potentially crystalline, because the phi i's are crystalline and the theta i's are potentially crystalline. And now we just choose the phi i's. It's easy to choose the phi i's such that the Hodge Tate weights are anything we like, anything that we want to prescribe. So in particular, we can assume we can prescribe the monotonicity. And we can prescribe that when we take the union of the sigma Hodge Tate weights over I, we get n minus 1 down to 0 for all sigma. Or any other set of distinct n integers that we like. Then Vi restricted. So Vi restricted to GKI is just a direct sum of conjugates of this character. And the last observation is that if we restrict to a further finite extension, we can make each of these finitely many ramified characters be unramified. Sorry, the theta i's are finitely ramified. So Vi restricted to GL is diagonal because, so for this we just need that L contains Ki and crystalline. For any L, a finite totally ramified extension of degree, the residue field of Ki. So it's easy to see by class field theory that if we take this finitely ramified character, tame character theta I, and we restrict it to such a totally ramified extension, that it becomes unramified. And the phi i's are crystalline, so together we get something crystalline. Yeah, so we get the lift of prescribed of Hodge type 0, which becomes crystalline over some extension that doesn't depend on rho bar. And the potential diagonalizability is clear, just as before. So we get the uniform K prime over K as in Theorem 1, part 2. And that finishes the proof of the theorem. Modulo the proposition. So in the last part of the talk, I'm going to discuss the proposition. So it's still there. So the proof is by induction on L, and I'll just focus on the case L is equal to 2, but the other steps are the same. So when L is equal to 2, we have rho bar of the form an extension of V2 bar by V1 bar, and we want to lift to rho of the form V1, V2, and we have to allow some twist, but we might as well just allow one twist, because otherwise we can twist the whole row. To be precise, for infinitely many unramified characters psi of gk with trivial reduction. And so we really play around with the field of definition of these representations. We first choose some finite extension over which we can realize everything. Let me call that E, the finite extension of QP, such that both the representations Vi are realizable over OE, and also the representation rho bar is realizable over the residue field, Ke. And now choose another finite extension. So this is finite. Choose another finite extension such that the ramification index of F over E is greater than the dimension of V1 bar times the dimension of V2 bar. And now we work over this extension F, so or rather the ring of integers OF. So when I write Vi, I just consider them. I consider a chosen model of V1 over OF and so on. So now we just it's a problem in Galois cohomology to lift such an extension. So we have the homomorphisms of V2 twisted by psi. V1, so this is OF homomorphisms, just to be clear. And psi also lives over OF. So then we have the reduction map to H1 GK homomorphisms over the residue field of V2 bar to V1 bar, because the character reduces to the identity. And now we have a map delta to H2 of GK in the long exact sequence OF V2 tensor psi V1. And we pass to the dual side by Tate local duality. We get delta check from H0 of GK homomorphisms of V1 to V2. How do I want to write it? V21 twisted by psi tensored by F over OF. So Pontryagin dual twisted by cyclotomic to H1 of GK hom KF. So the dual H1 in the middle, which is V1 bar V2 bar 1. And what we need is that what we need is that the kernel of delta, which are precisely the liftable classes, namely the classes that come from reduction from characteristic 0, the kernel of delta contains the peu ramifié classes, namely the annihilator of the unramified classes. So let me write it this way. Unramified classes annihilator. Equivalently, though, under duality, the annihilator of the kernel is the image of the dual map, and that should be contained in the unramified classes. So we are reduced to the following lemma, for which I make the definition X to be the homomorphisms from V1 to V2 twisted by 1. So here's the key lemma. Namely X, suppose that X is an OF GK module, which is finite free over OF and realizable over this smaller extension OE, realizable over this smaller ring OE, where the ramification index is as above, greater than the rank of X, which is here dimension of V1 times dimension of V1 bar times dimension of V2 bar. If the character is sufficiently close to the boundary of the unramified characters that reduce to 1, namely if psi evaluated at Frobenius minus 1 has valuation between 0 and ramification index divided by the rank of X. So the valuation is normalized such that the uniformizer of F has valuation 1. Then, one more assumption. X tensor psi has no GK invariance. Then the image of delta check is precisely the unramified classes. So image of delta check H0 X tensor psi tensor F over OF to H1 X tensor the residue field is ramified classes. So let me just write H1 unramified of the right-hand side. So this key lemma finishes us off because it shows that the image is precisely the unramified classes under this careful choice of extension and character. And clearly there are infinitely many choices for the character. Or even extension. Well, infinitely many choices of the character. So the final thing I want to say is why are Fontaine-Laffaille representations peu ramifié? So there's presumably a direct proof of this, but the way we prove it is using the key lemma. It has a lot of lifts by our, Fontaine-Laffaille, the idea is Fontaine-Laffaille representations have a lot of lifts to characteristic 0, so many that we can put ourselves in the situation of the key lemma to go back in this argument and deduce that we are peu ramifié. So do I have, I don't remember when I started exactly. I have about 2 minutes, maybe? Okay. So rho bar Fontaine-Laffaille, then it's easy to show. So it seems this was also observed by Kaloniatis in his PhD thesis in London right now, that, so this year I think, well, there exists Vi lifting Vi bar such that rho bar has lifts of the form V1 tensor psi 1 up to VL tensor psi L for all psi I as above. So all psi I that are unramified and reduced to 1. So this is very easy. You can just work on Fontaine-Laffaille in the Fontaine-Laffaille semilinear category. And if we go back to the L equals 2 situation, so we just choose the psi I as in proof I just gave, so that we put ourselves in the situation of the key lemma. So we choose the E and the F appropriately and then choose psi such that these conditions hold. Then the key lemma shows that the image of delta check is the unramified classes, and dually that the kernel of delta is equal to the pyramiphier classes. And by assumption, rho bar lifts to characteristic 0 in this setup, so it's pyramiphier. So, in fact, we did use that having many lifts with respect to psi i's that sort of get closer and closer to the boundary in a precise sense is equivalent to being pyramiphier. So let me stop here.